The planetary group is working up fervor inside the galactic local area. Ongoing reports indicate a potential encounter with Neptune, raising concerns among researchers and space lovers alike. Eminent specialists, including Neil deGrasse Tyson and Michio Kaku, have sounded alarms about the expected results of this divine conflict. Yet, how did Pluto end up on a crash course with its far-off neighbor, and how could this enormous crash affect us here on Earth? Let's investigate this unfolding event. Once viewed as an undeniable planet, Pluto was subsequently renamed as a dwarf planet due to its remarkable orbit. In spite of this change, it continues to enthrall and attract astronomers. Late forecasts from distinguished researchers highlight a troubling proximity between Pluto's path and that of Neptune. These specialists warn against a possible impact between the two planets, which could represent a significant danger to Earth. Pluto's journey around the Sun is marked by its unique qualities within our planetary group. Its orbit spans an extraordinary 248 years, and since its discovery in 1930, Pluto has yet to complete a full revolution. Adding to its intrigue is the highly elliptical shape of its orbit, a departure from the nearly circular orbits of the major planets. Furthermore, Pluto's orbit is tilted at 17 degrees to the ecliptic plane, making its path steeper compared to other planets. One striking feature of Pluto's orbit is its intersection with Neptune's path for about 20 years in each orbit. As Pluto ventures closer to the Sun, Neptune opposes expectations based on their respective positions in the nearby solar system. So, why hasn't a crash occurred between Pluto and Neptune? The explanation lies in the gravitational effects exerted by other planets. The study of Pluto's orbit began soon after its discovery, revealing a puzzling trajectory for astronomers. Unlike most of the planets, whose orbits align relatively closely to the ecliptic plane, Pluto's distinctive features include a steep inclination and an elongated shape. The mystery deepened with the realization that Pluto's orbit crosses that of Neptune. The stability of Pluto's orbit, amidst these complexities, serves as evidence of the intricacies inherent in space mechanics. The three-body problem in space involves understanding the motion and gravitational interactions between three celestial bodies, such as Pluto, Neptune, and the Sun. This problem explains the complex dance of their paths and gravitational forces. Terms like soul libration, scope libration, and the V's-K oscillation help untangle this cosmic riddle. Astrophysicists claim that soul libration, responsible for maintaining planets in their orbits, plays a critical role when it comes to Pluto and Neptune. This term suggests that when Pluto crosses Neptune's orbit, it is situated no less than 90 degrees away from Neptune, thus preventing potential collisions. Scope libration ensures that when Pluto approaches Neptune or other giant planets, it is positioned significantly above their orbital plane, providing an extra layer of protection against crashes. The V's-K oscillation explains why Pluto's orbit around the Sun appears erratic, but remains stable over time, despite apparent unpredictability in space. Mathematical simulations in the late 1980s revealed that, despite Pluto's stable properties, its orbit is, in fact, turbulent, with minor initial deviations leading to huge differences over thousands of years. However, Pluto's unique orbit maintains stability over extraordinarily long timescales, holding disorder in check. Recent computer models have enhanced our understanding of how large planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune's unique relationship with Pluto, completing 3 orbits for every 2 of Pluto's, contributes to the stability of Pluto's orbit. Additionally, Jupiter's immense gravity exerts a significant impact, while Saturn's influence, though smaller, also plays a role. Through comprehensive studies, scientists have shown that the combined effects of Neptune, Jupiter, and Saturn ensure the safe and stable movement of Pluto through space for billions of years. These phenomena are crucial for maintaining order and consistency in celestial dynamics. Without these forces, the solar system would be prone to greater chaos and instability, potentially leading to collisions or ejections from stable paths, causing cascading effects on other celestial bodies. Understanding Pluto's orbit is particularly important in discussions about a potential collision with Neptune in the future. This knowledge provides a clearer understanding of the dynamic nature of the nearby solar system. Pluto's case highlights the fact that seemingly unstable orbits can reach equilibrium through the intricate interplay of gravitational forces and orbital mechanics. Ongoing observation and analysis of these phenomena are essential for gaining a better grasp of our place in the universe. Exploring the depths of space often reveals the unpredictable nature of celestial bodies, and Pluto's orbit serves as an excellent example of this capriciousness. The concept of orbital turmoil distinctly illustrates the delicate dependence of a celestial body's path on its initial conditions. As shown in Pluto's case, even slight variations in the dwarf planet's position or speed can significantly alter its long-term orbit. Programmatic simulations have been instrumental in helping scientists understand how Pluto moves in space. By making small adjustments to these simulations, space experts can observe what minor changes can have a major impact on Pluto's trajectory. In the late 1980s, these simulations uncovered an interesting aspect of Pluto's orbit. Despite features like soul libration and scope libration contributing to its stability, Pluto's orbit can still exhibit unpredictability. Even a tiny initial difference in Pluto's position or velocity can lead to substantial changes in its path over many years. Despite this inherent chaos, Pluto's orbit remains stable over an unusually long period, extending over billions of years. This suggests that beneath its seemingly erratic appearance, Pluto's journey around the Sun follows an organized pattern, anticipating vast events. Predicting future paths of celestial bodies, especially those with eccentric orbits like Pluto, is very difficult. The inherent unpredictability of these systems makes long-term predictions uncertain. Mathematical simulations help us understand and forecast the future movements of celestial bodies, but they also reveal the limitations of our predictive capabilities. These models heavily rely on precise initial conditions and simulate complex interactions. Even a small error can lead to dramatically different outcomes, making accurate predictions challenging. The tumultuous nature of celestial orbits, such as Pluto's, reminds us of the ever-changing universe. While we have made progress in understanding space, Pluto's case underscores our still limited knowledge. Understanding the gravitational effects of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can influence the stability and trajectory of other bodies in the system. Despite these complex forces, leading astrophysicists are expressing concerns about a possible crash between Pluto and Neptune, raising questions about why such a collision, which seems unlikely given these intricate dynamics, is now a subject of concern. Neil deGrasse Tyson, a renowned astrophysicist, offers a unique perspective on the mysteries of our solar system, especially with regard to Pluto. Tyson, famous for renaming Pluto as a dwarf planet instead of a major planet, shares thoughtful reflections on how our understanding of celestial mechanics is constantly evolving. He views Pluto's renaming not as a downgrade, but as a necessary adjustment to our growing knowledge about the various objects orbiting the Sun. His approach to celestial mechanics involves continuous learning and adaptation. He sees the complexities of orbits like Pluto's as a sign of how much more there is to discover in space. Tyson believes that the allure of these objects is what makes astronomy so fascinating. He is also aware of how space-related events and discoveries capture the public's imagination. He considers occurrences like Pluto's renaming and its peculiar orbit as opportunities to engage the public's curiosity and interest in science. By exploring the dynamic and sometimes unpredictable aspects of space mechanics, Tyson aims to foster a deeper understanding and appreciation for the universe. Tyson opens a window for the public to wonder at the marvels and mysteries of the universe. Working alongside other scientists, Tyson effectively alerts the public about the potential dangers of Pluto's eccentric orbit. After extensive study of Pluto, he has raised concerns that the three-body problem could pose a real threat, suggesting that a collision with Neptune is long overdue. Moreover, Tyson emphasized how such a collision could disrupt the balance of the universe and lead to catastrophic consequences extending to Earth. A crash between Pluto and Neptune would be an unprecedented and devastating event in our solar system. This impact would release a tremendous amount of energy, likely disintegrating Pluto due to its smaller size and icy composition. Debris from the collision could scatter across the solar system, posing potential risks to other planets and their moons. For Neptune, such an impact could potentially alter its atmosphere and orbit, depending on the specifics of the collision. Michio Kaku, a renowned theoretical physicist recognized for his work in string theory and science advocacy, offers an intriguing perspective on this scenario. His views on the future of space exploration and the connection between celestial mechanics and theoretical physics are instrumental in understanding the complexities of the universe. Kaku's insights into the potential consequences of a Pluto-Neptune collision align with his broader understanding of the universe's laws. He emphasizes that the interconnectedness of celestial bodies and their gravitational influences is a delicate balance. Even small changes in a planet's position or orbit can have cascading effects across the solar system. According to Kaku, a catastrophic event, such as an impact between Pluto and Neptune, could not only disrupt the orbits of these planets, but also reverberate throughout the entire solar system. The effects could range from alterations in the orbits of nearby planets to the destabilization of moons, or even possible changes in the gravitational relationships that bind the planets together. Kaku's expertise in theoretical physics also allows him to explore the potential outcomes of such a crash from a multiverse perspective. If the collision were to create a significant disruption in the solar system, it could have a ripple effect on the fabric of space-time itself. This could potentially trigger larger-scale changes that extend beyond our immediate solar system, affecting the dynamics of neighboring star systems. Moreover, Kaku stresses the importance of ongoing research and simulations to better understand the complexities of space mechanics. He believes that advancements in computational models will enable scientists to predict with greater accuracy the potential outcomes of interactions between celestial bodies. These simulations, he argues, are critical for not only understanding Pluto's peculiar orbit, but also for developing strategies to protect Earth from unforeseen cosmic events. As for the broader implications of such a crash, Kaku reminds us that we are still in the early stages of our understanding of space. While our knowledge has expanded significantly in recent decades, we are still discovering new details about our solar system's inner workings. The idea of a collision between Pluto and Neptune may seem far-fetched, but it underscores the unpredictable nature of space and the importance of remaining vigilant as we explore the cosmos. In conclusion, while the possibility of a Pluto-Neptune collision remains uncertain, the complexities of orbital dynamics and gravitational interactions continue to captivate scientists and the public alike. Researchers like Tyson and Kaku are leading the charge in unraveling these cosmic mysteries, urging continued observation and exploration. By studying Pluto's orbit, we gain valuable insights into the nature of the solar system and its potential future. Ultimately, the study of these phenomena not only enhances our understanding of space, but also serves as a reminder of the vast and ever-changing universe in which we live. As our knowledge of space continues to evolve, so too will our ability to predict and